Today, my goal would be to show how we get, starting from a relativistic Lagrangian, how we get to a Lagrangian that looks like what Professor Daniel and Professor Kaplan has shown. So something like psi dagger I del t minus del square by 2m plus some potential psi. So how do you get this Lagrangian starting from a relativistic theory? So just to set up the background, we already know, I'm doing NREFT. So we already know two types of EFT category, which is top-down and bottom-up. And NREFT are basically sitting in the top-down approach in the sense that you have a UV theory to which you can match onto to get your matching coefficients or the Wilson coefficients. Examples of the bottom-up are something like chiral perturbation theory, where things are non-perturbative and you start constructing from bottom-up approach and fit parameters to the experiments. So to arrive at this, there are a couple of ways one can do. There is something called as non-relativistic reduction. So I will go over it for both scalar and fermions. What I mean by the fermion case is that starting from the Dirac-Lagrangian or Dirac equation, doing this non-relativistic reduction, so NR, we get the Pauli equation. And the other way that we will see today, if time permits, is the matching calculation. So I won't go into any loop level matching calculation. I will just show you the tree level matching calculations. And further down the lectures, we will see similar matching calculations in the context of heavy quark EFT or non-relativistic QED. Okay, so just separate out the things. So the point is, let me start first with the Klein-Gordon equation or the Klein-Gordon Lagrangian. Where the dots mean any higher order terms that I want to add, but let's keep up to phi-4 theory. This phi is my scalar field. For simplicity, I will focus on the scalar, on the real scalar field, sorry. So for simplicity, I will focus on the real field, but you can do the same approach to the complex scalar case. Do a non-relativistic reduction so that we can arrive at this Lagrangian. So our approach is to go from here to this. For the time being, just I'll try to be systematic on how you arrive it. So let me define a field redefinition. Which is relating phi x of t to a field psi. Okay. This field redefinition is at tree level in the sense that I can define more complicated redefinitions where I can include higher and higher order terms in the momentum over mass expansion. And when I say non-relativistic, my goal is I'm looking at energy scale or momentum scale much less than my mass. So this is my mass of the scalar field here, and I want to construct an EFT for energy scales which are much less than the rest mass of the system. So we know from the scalar field theory that the energy of this particle phi from the dispersion relation is just square root of m square plus p square, which in the p less than m expansion would give me something like m plus epsilon E and R, which is defined to be this expansion where I basically define this piece as my epsilon E and R, okay? Now, the thing is, why do I write this? So the question now what you're wondering is, why do I write this relation for the non-relativistic reduction? I mean, what forced me to make this definition for constructing the non-relativistic EFT? And that has to source from the mode expansion of the phi field. First of all, you should note that with this definition, I constrained that phi dagger is phi. Okay, it has to be Hermitian for the real field. Complex field, it would be slightly different. And the point is, if I look at the mode expansion of the phi, which we study in like Peshkin or any other UFT book. So this is my 4 vector, okay? This P dot X is my 4 vector, it's not the 3 momentum. So maybe I should differentiate like this. What happens is that if I use this expansion here, I can expand my this term in the exponential as something that oscillates, that includes a term with the rest mass and something that gives me the rest which gives me the non-relativistic piece. So if I use this expansion that I wrote here, for example, let's say in equation 1, things like this can be expanded as something like E. And if I use it here, I immediately extract out my piece, which is corresponding to the rest mass piece, and rest is the usual one. And you can do it same for the AP dagger in this term. And so what happens is that the point is there is a order P over M expansion that I'm not worried about right now. So what happens is that my phi of X, and there is this 2EP here that also breaks down. So the 2EP is 2M plus order P over M in the expansion. That breaks down to 1 by square root of 2M. I factor out this piece. Maybe let me just write the first term and then I leave it else. Plus the Hermitian conjugate. So looking at this expression and this expression, this is my psi that I have defined, or this is the piece that I have defined my psi as of xt. Okay, so I've done nothing else. I have just taken the mode expansion of the real scalar field, expanded in terms of the momentum by heavy quark mass or massive particle mass, and extracted out a highly oscillatory piece that would correspond to the rest mass. Because in this exponential, this would be the term that would be oscillating over time scales at much smaller times. This would be oscillating very fast or very rapidly compared to this term in the exponential. Now, yeah, psi is the non-relativistic complex field. Okay. Sorry? The Hermitian conjugate will give me the psi dagger. So this piece would give me the psi star or psi dagger. What did I write? Sorry. Would give me the psi dagger. Okay. So first question for you is phi is a scalar, psi is a complex. What is happening on? Is there something that people are, is there something happening to the degrees of freedom? Because a real scalar will have only 1 degree of freedom, whereas a complex in general would have 2 degrees of freedom. And so going from relativistic to non-relativistic, did we switch to like increase the number of degrees of freedom? Sorry? Yeah. Which complex part? Yeah. No. I mean, the thing is the Lagrangian has a psi dagger term. The Lagrangian does not. I mean, so, okay, so let me, before answering that question, the Lagrangian that for the phi 4, if I use this, sorry if I have to use another piece of chalk just for the coloring. So as an exercise, this is something that you can do. This is a pure algebraic question, pure algebra. So you use this, substitute it here, and remove terms that are highly oscillating in terms, highly oscillatory in this e raised to minus imt factor, throw them out because they won't contribute, they would average out to 0 in the case of action. And the Lagrangian that you are end up getting is something like I by 2, or let's not confuse it, I m del square psi minus so how did so let me just outline, because I will leave this as an exercise for you. This is a simple exercise, just involves algebra. So you start with the action, which is L times d4 of x. Okay. You start with the action, which is L times d4 of x. Now, in the scalar Lagrangian, you substitute this expansion. In the action, we have an integration over time t. You would end up getting certain terms with exponential of imt or twice of imt or something. But those are, since highly oscillatory terms, you just average out to 0, and you only include terms which does not include those pieces associated with the rest mass. And this is the Lagrangian that you would end up with. Now, coming back to your question, we started with a real scalar field, but we are ending up with a non-relativistic Lagrangian that has a complex scalar field. So what has happened? What has changed in the case of real scalar to the complex, from the real scalar to non-relativistic complex? So is the time derivative the same order of magnitude? Is the time derivative the same in both the real and the complex, in the relativistic Lagrangian and the non-relativistic Lagrangian? No. So the time derivative in the real in the real scalar case is 2 time derivatives. Whereas here in the non-relativistic case, there is only one time derivative. And this has impact in the sense that this only describes degrees of freedom propagating for like particle or antiparticle, but not both. So the two-time derivative gives me a Klein-Gordon equation for which the energies I would get would correspond to both particle and antiparticle. Here, I only have one time derivative, which would correspond to 1 degree of freedom. So in general, basically, in general, it is counterintuitive. Not explicitly, but I mean, so the way the thing happen is that in general, any relativistic Lagrangian that has two time derivatives, the number of propagating degrees of freedom are equal to the number of real fields. Whereas in any Lagrangian with one time derivative, the number of propagating degrees of freedom are half the number of real fields.
How do you see it?
Mathematically, I don't have an answer. It's first order in time. It's only describing either particle propagation or antiparticle. Not giving you two poles, but only one. That's the point. Yeah. Yeah. Yes. Exactly. Yes. And the way, like what Namit is explaining is, here if I compute the conjugate variable for psi, this is just, the pi is just psi dagger, whereas there it would be a phi dot, and phi dot are independent variables. So an observation that I would write is it's counterintuitive for a real scalar non-relativistic limit to go to a complex scalar. Second, for Lagrangian with two time derivatives, number of degrees of freedom is number of scalar fields, number of real scalar. And Lagrangian with one time derivative is number of degrees of freedom is 1/2 number of real scalar. Okay. So for a complex field, I need two scalar fields, two real scalars. In the non-relativistic case, because there is one time derivative, it eventually goes down to 1 degree of freedom. Now, extending all this idea to non-relativistic scalar, to complex scalar field is also very simple. So, so in the case of complex field, the phi is which is the mode expansion of the phi in the QFT. This in general describes your particle, and this will describe your antiparticle. What we will see in the case of NRQED or other cases like in the heavy quark system is you define basically two fields, non-relativistic field. So define for this a non-relativistic field psi, and here non-relativistic field chi. This would be a little bit apparent in the next few lectures or or so, or when I discuss the Pauli spinor case. So the point is, in this case, the observations are, we define two separate fields, psi and chi, for particle and antiparticle. And the second point is that the number of particle or number of antiparticle in the non-relativistic EFTs are always conserved. Anybody has, can anybody explain why? So because we have gone at energy scales less than the rest mass of the particle or antiparticle, particle creation or particle annihilations are not allowed in EFTs, non-relativistic EFT, which means there cannot be number violating processes in the effective field theory. There is alternative way how you, if you want to do such studies, there's alternative way in which you can account for number violating processes, but in general, particle creation or particle annihilations are not allowed in NREFTs. So particle creation and annihilation are not allowed. In an REFT, which means number of particle associated to psi and number of antiparticle associated to chi are conserved. So these both are conserved numbers. Okay. The momentum is much less than the mass of the rest mass of the particle. Okay. So in order to create the particle, I at least need the rest mass, and my energy scale won't touch it in the non. So I would have a U1 symmetry in the non-relativistic EFTs that would allow for the particle creation, particle number conservations for both particle and antiparticle. As a simple example, okay, this I'm talking in with respect to complex scalar. Even in the case of real scalar here, I have, if I write a numbered operator, which is D3 of R psi dagger psi, this is conserved. And this is corresponding to a U1 symmetry of EFT. Now, is that symmetry present in the case of complex, in the presence of, is that symmetry present here? The answer is no. This is an emergent symmetry of the non-relativistic EFT, which is absent in the case of the full theory, but now is present in the case of non-relativistic EFTs. So that's why in any time you go into non-relativistic theories, your particle number is conserved, or if you have antiparticle, your antiparticle number is conserved. You do not have any particle creation or particle annihilation. So the number of particles coming in has to be the same as the same number of particles going out. Yeah. Exactly. Yeah, for example, in the case of fermions, in the case of heavy quark bound states, I would have a particle corresponding to a quark. The anti-quark is my antiparticle. So I will talk to it in the case of Dirac, in the case of the non-relativistic EFT for the Dirac-Lagrangian. So your heavy quark, your charm quark is your particle, your anti-charm is your antiparticle now. That is the thing. Yeah. Yes. I mean, the point is, in the case of like Dirac-Lagrangian, you have both particle and antiparticle. Yes. So again, if you go to like something like in the case of charm, there is a charm and anti-charm. And now in non-relativistic EFT, I am now describing a field propagating for charm and another field propagating for anti-charm. They are not related by charge conjugation. It's a different field now. Yeah, the annihilations are accounted through non-Hermitian operators. So just like in cold, just like in cold atoms, we have these three-body recombination rates. So there you make your Hamiltonian non-Hermitian, you account for these non-Hermitian terms into Lagrangian. That will not describe. That will describe something like loss processes or annihilation processes. So no, so those, I mean, they can contain. So for example, this can describe, let's say, a CC bar annihilation to some final states. And the way you account for these annihilation is you add some non-Hermitian term into your Lagrange. But you have to fit it here. So in simple case, for example, let's say I have, so for example, here, I do not have number conservation. I can have as many number of phi's. I can have 4 phi's coming in and then 2 phi's going out. So if I have 4 non-relativistic phi's coming in, the 2 phi's that are going out are relativistic. So if I create my, let's say, an experiment with lasers and all that, I start with a non-relativistic atoms that are described by this phi field. Eventually the 4 phi will come in. There will be two phi's going out, which are relativistic. They will be moved out of the trap. And the way you account for them is you add a non-Hermitian term into your Lagrangian. They will come from these one loop diagrams. Okay. In the full theory, you compute these one loop diagrams, make a cut, you find a contribution from the imaginary part. And those imaginary part will give you the non-Hermitian terms into your EFT. If people are interested, we'll go into it as an example, but I would not go right now. Yeah. So the term that is added to your, like just exactly. So the term that is added to your, the non-Hermitian term that is added to your effective Lagrangian, in plain quantum mechanics, if you take the mod psi square, would mimic the exponential decay. Exactly. So, so that's, yeah. Elastic channel, yes. So basically something like, think of like I create a trap of cold atoms. I have started with like 5 atoms, but then because of interactions, 3 of them are lost. So they are gone to the environment. The way I account for this loss process is by adding a term. In quantum mechanics, you would say that mod psi square falls off like this. This is the term that I would exactly add to my Hamiltonian in EFT to make it non-Hermitian. So the simple way you see it is that my psi would go as exponential of minus IHT. I would make my H to H minus IK or something. And then when I compute the probability, this gamma would be related to this K. Okay. This is the way generally we do it. Yeah. I mean, I can do phi cube. I'm not considering the, I mean, I started with a simple example. So could you repeat again? The phi cube will break Z2 symmetry. Okay. Yeah. For a Hermitian conjugate. Yeah, Hermitian conjugate would enter. So you would have to break Z2 symmetry. You'll have a term corresponding to Z2. Yeah. So there is, phi is the relativistic theory. Yeah. Yeah. No. So in the relativistic complex scalar, when I do the mode expansion of phi, there is a piece corresponding to particle, and there's a piece corresponding to antiparticle. Okay? Yeah, I mean, the thing is, it depends. Yes, phi will annihilate a particle, but create an antiparticle. The phi star will create a particle, but annihilate an antiparticle. It has same meaning. I mean, it's just, you look at it in either way you want. Yeah. So you have this term. Yeah. Yes, I won't have Lorentz invariance. As soon as I go to non-relativistic theory, Lorentz invariance is broken. So there is a way, okay, maybe we'll not discuss it. We'll discuss in the later lecture. So for example, in heavy quark EFT, the way you map onto Lorentz invariance is through something called as reparameterization invariance. But ideally in non-relativistic theory, Lorentz invariance is broken. You just have Galilean invariance. You have Schrodinger symmetry or Galilean symmetry. Leaving is from top to bottom. It's not from going from bottom to up. It's from top to bottom. I have a Lorentz invariant theory. I want to start with the relativistic theory and I want match to the non-relativistic theory. So this is the point. So any calculation I do in the EFT, I'll actually match onto full theory. I'll start with an example soon. Okay, so no. So the normalizations and all will have a little bit of subtlety, like, no. I mean, maybe I can discuss the normalization part. Oops, sorry. So, okay, good. So I'm arriving at that point. So in this case of complex scalar, so I'll discuss that subtlety part a little bit. So in the case of complex scalar, so non-relativistic EFT, so I'm describing complex scalar here because eventually this is what I will use for my Dirac theory. That is where the connection might be more clear. So my complex Lagrangian of non-relativistic theory would look like okay. Then there could be terms like psi dagger psi, chi dagger chi, and so on. D is having some dimensions that would give me the correct mass dimensions and everything. So we'll see about it later. So this would come from a complex Lagrangian. So that is my del mu phi star, del mu phi. Something else. If I do non-relativistic reduction, this is what I get. Again, this is left as an exercise for you. It's just pure algebra, so nothing to be learned much about here. Okay, so an important aspect that also, if you look at from the normalization side or the mass dimensions, that also gives an answer why I need this 1 by square root 2m factor, this piece to match my non-relativistic fields phi to my non-relativistic field psi. In general, no. All the symmetry of QCD has to be the symmetry of EFT. So in general, no. Yes. I mean, you are starting with a QCD theory and then you are going to a low energy theory of QCD. So your symmetry of QCD should be carried out to the EFT theory. Okay, so if I do the mass dimensions, so this will also touch upon what Professor Daniel or Kaplan did on the first day, probably. The field phi has mass dimension of 1, which means, so let me just write it here. Just take an h bar equals to 1 or non-relativistic, okay? So the field phi has mass dimension 1, which is L inverse in terms of the length scale, okay? I will write in terms of the length scale because that will be easier for me to connect to the non-relativistic EFT. The Lagrangian density is L raised to 4. The time and the x is L raised to 1 here, okay? Now, in non-relativistic case, the Lagrangian is, so we start with the action again. My x goes as L raised to 1, my time goes as L square, okay? This is because my h bar is 1 and m is just a parameter in the non-relativistic theory. So time is L square, which means my Lagrangian is L raised to minus 5. Everybody clear about this? Yeah. Yeah, minus 4. Thank you. Yeah. And if I use my Lagrangian here, non-relativistic Lagrangian here, this or the Lagrangian for the written there somewhere, what you would find is psi is L raised to minus 3/2. Okay? Yeah, thank you. Yeah. Thank you. Yeah, sorry for the sign error. Yeah. So the psi scaling is L raised to minus 3/2. This is also consistent with the fact that I told you that number is d3 of x psi star psi. So number is a number which is dimension of L raised to 0. So psi will again come back to the L raised to minus 3/2 factor. And this immediately tells you that a field phi whose dimension is L raised to minus 1, I have to relate to a field psi whose dimension is L raised to minus 3/2. The only way I can account for is I multiply by a root m factor in the relativistic theory. Because in the relativistic theory, m is L inverse, whereas m is just a parameter for me in the non-relativistic theory. And that matches out my dimension analysis from the dimensional side. So this basically tells me that phi is some field proportional to psi 1 over root m. The 2 is coming because of there is a 1/2 EP that we saw in the mode expansion. But this is the argument roughly that why there is a 1/m factor or square root of m factor in the case of non-relativistic theories. You can see the same thing from the normalizations of the states. So maybe let me erase a part a bit. Or can people see here? Or maybe it is better there. Better there. Okay. So in relativistic theory, my field or my states are normalized as okay. Whereas in non-relativistic theory, so I will write it as k just to differentiate, is 2 pi cube delta Q K minus K prime. Now, a naive comparison between the two would tell me that that P, which is my relativistic, is something like, so in P tending to 0 limit, this is 2m, is square root of 2m K, okay? And the way one can see this, why this relation holds is again going back to the mode expansion. Yeah. Yeah, the K is a 3-vector K. They're all 3 vectors. Yeah, all 3 vectors. Yeah, this is the usual case. So the way we can see this is directly using this equation. Fine. So if I use this mode expansion of phi, this is my operator. A is my creation. A dagger P is my operator that creates my one particle state. So this is something like A dagger P vacuum in the relativistic theory. But in the non-relativistic case, the operator that creates the one particle state is so let me just write an expression here, is something like a BP dagger, which is defined to be a AP dagger over square root of 2m. Okay, so you just take this expression here. After extracting out this 1 by square root of 2m, the operator that creates a one particle state is this P. Okay, so this is something square root of 2m B dagger P vacuum, but this is non-relativistic vacuum. This is relativistic vacuum. And so this immediately tells you that, yeah, so that the square root of this condition is satisfied. So on both sides, so this equality here really means a matching in some sense. You should not think of equality like real equality because they are working on two different Hilbert space here. On one side, we have a vacuum of the relativistic theory. On another side, we have a vacuum of the non-relativistic theory. The equality is in some sense that we are matching the one particle state on the relativistic theory to the non-relativistic theory. And from the normalization side, that also explains why there should be a square root of 1 by square root of 2m. Okay. That's kind of wraps up the whole picture in dimensional analysis and the normalization. Yeah. Yeah, I mean, there is it's a Hilbert, it's a completely different Hilbert space now. It's not, yeah. Yeah. That's why I told you this equality should be thought of as in a very careful sense, not the equality in the true sense. It's equality from the matching sense. Okay, so now, yeah.
Omega 1 equal to 1 in both.
Generally, I have not seen people relating to omegas because in one case you are allowed to have. What omega? What is the omega you are? Yeah, okay, okay, yeah. Yeah, you can, yeah. Okay, so this was the whole story for the kind of the real scalar field, okay? Now the goal is to go from Dirac equation to the Pauli equations in the non-relativistic limit, because that really tells me why I want to do all these NRQET type of business, and that it gives me the Lagrangian or the equations of motions for the Schrodinger equation of a spin half particle propagating in the electromagnetic field. So that's the Pauli equation that we see. So I will start from here. Oh, sorry. Yeah. This is my Dirac equation where the gamma zero, the gamma matrices are in the Dirac basis. So I'm defining everything in terms of Dirac basis. because I would work in the Dirac basis only and not like in Weil or Majorna basis or anything, because this is the basis where we could see the direct connections with the particle and antiparticle in this spinor sense here. So you would have 1, 0, 0, minus 1. You have gamma I, which is 0, sigma k, minus sigma k, 0. And now the goal is, like I said, to go from Dirac equation to an equation that looks something like that you have studied in normal electrodynamics also, P minus E square by 2m plus some terms acting on psi to be 0 or something. Get some type of this Lagrangian here or equation. So again, I start with my Dirac field psi. I would use the notation that I have introduced in the complex scalar just for consistency. I define two Pauli spinors. So Dirac is 4 cross 4. This is 2 cross 2, 2 cross 2. And I would again expand out the fast moving modes. So by yeah, okay. So let us look at, say, positive energy solutions. So everybody recall what is positive energy solutions for the Dirac equation? Anybody has any questions? They may be to ask. So this is my, like, the U vector that we define, U of P or something. So the positive energy solution is, I look at the positive, but you can do it also for the negative energy solutions. And again, I expand my EP to something like M plus T here, which is my E epsilon NR, or let's say I use epsilon NR here. And the thing is, for such positive energy solutions, so as an example, if I take for positive energy, so for such positive energy solutions, one of the Dirac spinor is something like 1, 0. Let me just have a look. Yeah. So first, so the point is to explain why there is two component Pauli spinors are appearing. So for such one, if you take the positive energy solutions, U of P, and take the non-relativistic limit, P much less than M, which is in simple way taking P tending to 0 and M tending to infinity, for example, what you end up getting is something like 1, 0 and 0 here for both the parts. Okay. Yeah, this is 4 cross 1. This is the Dirac spinor I'm starting with. Oh, my mistake. Oh, I'm sorry. Thank you. Yeah. So, and same if I do it for the negative energy solutions or the other solutions, so call it U1, U2, which has 0, 1, and some terms depending on momentum. This would directly give me 0, 1, 0, 0. So basically this spinor here, this part here, and this part here are describing my particle with spin 1/2 and particle with spin -1/2. I'm talking about the Z projections here, okay? Now, if I do the same thing for the negative energy solutions, V of P, what I would have is some, let me write one case because then it will be, so this reduces down to 0, 0, 1, 0. And this is something like same thing would reduce down to 0, 0, 0, 1. Again, this two lower blocks are describing my antiparticle with spin projections +1/2 and spin projection -1/2. And this is the reason why I am trying to break up here my Dirac spinor, 4 cross 1 component Dirac spinor in terms of psi and chi. where my psi is now a field corresponding or a two-component spinor that describes my particle projections in 1/2 minus 1/2, and chi is something that describes my anti-particle in projections with 1/2 and minus 1. So if you start with the positive energy solutions of the Dirac spinor and write the Dirac equation for this, what you end up getting is the equation you start with is P slash minus M UP is 0, or P slash minus M psi is 0. If I break it in terms of, if I use this expansion here, or if I write in terms of this piece here, so let me call it equation 2. If I use my equation 2 and try to simplify my Dirac-Lagrangian, what we will have is, let me see what I've called it. So I will have psi EA0 psi plus sigma dot P minus EA. So you have to use these Dirac bases for the gamma matrices, okay? There's an algebra thing, and so I leave it to you. Yeah, this is one equation that you will get. And the another equation that you get is 2m plus epsilon nr chi EA0 chi plus sigma dot P minus EA psi. Okay. So I started with my positive energy solution equation for the Dirac spinor, and I ended up getting these two equations. This factor of 2m, as you will see in heavy quark EFT, has very crucial importance, because that is what we will try to integrate out when we try to do the matching in the heavy quark EFT. But for the time being, let's try to see what is the result that we get. So epsilon nr is my relativistic energy going as m plus ENR. Yeah. So I do the expand, again, I demand that I want to work in the non-relativistic limit, which I demand that m is greater than epsilon nr. It is momentum, and it is greater than any of these electromagnetic field components. And so in that limit, what will happen is you will simply get 2m chi as sigma dot P minus EA psi, and that immediately tells you that chi is sigma dot P minus EA psi by 2m, which means this is of order 1 over m. Note, this is the anti-particle component of a positive energy solution of the Dirac spinor, okay? This is describing this chi field here. We will have a well definition in the heavy quark EFT that this would be the excitations of the anti-particle coming from the positive energy solutions of the Dirac spinor. I mean, this is my, I'm working in the limit. So this allows me to only keep this term and throw out this term and that term. The energy, potential energy, is the potential energy. Yeah. Yeah. So the thing is, immediately as you do if you do this chi thing, yeah. So now as we got this order 1 by m definition, if I substitute it back here, sorry, and you have to use this sigma dot A, sigma dot B of the Pauli matrices relations, which is A dot B identity plus I cross B. To simplify, what you would immediately get is epsilon nr psi is EA0 plus P minus, yeah, okay. P minus EA square by 2m plus I times dot sigma by m. by 2m times psi. And the thing is, this already looks like the term that we want there. Now, what happens to this term? This term will basically give you a spin interactions, because you can massage this term. You can write this as something like, so there's a factor of I minus E somewhere, so I'm sorry if I missed it, but so you can massage this term and write this as I minus E P cross A dot sigma over 2m. And if you identify with minus I del, this will directly give you a B field. Okay, all clear up to now? So the point is that the equation that I end up getting is epsilon nr psi P minus EA square over 2m minus E over 2m sigma dot B plus EA0 psi. And this is basically my Schrodinger Pauli equation. Okay, yeah. Exactly. This is what I was going to say next. Thanks. Yes, good. So basically, this immediately tells you, yeah. So like Professor Daniel predicted, if you take this term and associate it with the magnetic moment of a particle, of a fermion in the case of magnetic field, you would conclude that for a fermion, spin half fermion, this G is 2. The G factor is 2. And because you would identify the magnetic moment with E, yeah, let me just check. E spin over M, which is G times ES over 2M. And this is sigma over 2. So this is the Dirac prediction on the electron G G factor for electron, muon, or anything. Just comes out to be 2. Now, I would request you to please carefully go over this particular part on the Dirac-Lagrangian thing, because this would come back in the case of heavy quark EFT. When we go over it, this is exactly similar procedure that we will end up doing. And the goal would be to end up getting some Lagrangian that would look like here is the equation of motion I wrote, but the Lagrangian would be corresponding to this equation that I would try to get. So I think that ends my time here. Tomorrow, I will start with first showing a simple matching calculations in the real scalar field for relativistic theory and non-relativistic theory, and show you a clean example where sometimes this non-relativistic reduction might fail. And that is where the matching is really powerful. And then proceed on to heavy quark EFT and non-relativistic QED. So thank you.